Assalamu alaikum dear student. This is Wajid Risha and today we are going to discuss the topic self-induced EMF and self-inductance, which is given on page number 157. The definition of self-induced EMF is like the EMF induced in a coil due to the change of its own flux linked with it is called induced EMF. The EMF induced in a coil due to the change of its own flux linked with it is called induced EMF. Dear students, as we have already studied that when the conductor is stationary and the field is changing, then the EMF induced in the conductor is called statistically induced EMF. Self-induced EMF is an example of the statistically induced EMF. This figure shows the current carrying coil and a magnetic field established through the coil. If the current in the coil changes, then the flux linking the coil also changes. Hence, the EMF is induced in the coil. This is known as self-induced EMF. Okay. The direction of this EMF, it is by Lenz's law, is such that it opposes the cause of the generation of the magnetic field. The self-induced EMF will persist so long as the current in the coil is changing. So it is concluded that when the current in a coil changes, when the current flowing through the coil changes, which is shown by the indication of this galvanometer. So, if the current flowing through this coil changes, this magnetic field induced will also be changing, and because of the change of this magnetic field, an induced EMF will be produced here. So, this is self-induced EMF. It is concluded that when the current in a coil changes, the self-induced EMF opposes the change of the current in the coil, which is known as the self-inductance or simply inductance or induced EMF. So, from this diagram, we can see that the EMF induced in a coil due to the change of its own flux, this is the flux induced by the coil itself with the flow of the current. Linked with it, this is called induced EMF. The inductance of the coil can be demonstrated by changing current in it. For example, if a steady current is flowing in a circuit, there will be no inductance. If, for example, we introduce a DC source into this coil, like we have inserted a battery, a DC source. So by insertion of this DC source, the current will start to flow through the coil, but still there will be no self-induced EMF because the current is not changing its magnitude and the direction. Similarly, this magnetic field will also not be changing its values or direction, and no flux changing will take place through the coil and no self-induced EMF will be there. However, when the alternating current is flowing in the same circuit, the current is constantly changing and hence the circuit exhibits inductance. Let's say, for example, if we introduce an alternating current source to the coil. So what happens next? Because it is alternating current source, so every time the polarity, the magnitude of the current will be changing with respect to time, which basically changes the magnetic flux through the coil, and a self-induced EMF is generated in the coil, which is shown by the indication of the galvanometer. Now, let us move forward. What is self-inductance? What is actually inductance? Inductance is the property of the coil that opposes any change in the amount of the current flowing through it. Inductance is some sort of the resistance to the flow of the current. So simply, with the property of the coil that opposes any change in the amount of the current flowing through it. For example, if some amount of the current is flowing through the circuit, like in the previous diagram we have explained, and if we want to change the magnitude or direction of that current, so inductance of the coil basically resists that change of the current. This property is due to the self-induced EMF in the coil itself by the changing current. In order to find the expression for magnitude of self-induced EMF and self-inductance, consider a coil of N turns carrying a current of I, as we have previously discussed in the diagram. For example, if we have N number of turns in a coil and we want to introduce some AC current into that coil, so self-induced EMF will be there, and here we are going to derive an equation for the self-induced EMF for self-inductance. So, for example, EMF, as we already know that from Faraday's law, that EMF is equal to N delta phi divided by delta T, which we can already write like, we can write this N, which is a constant value, inside the brackets with this flux phi. So this is called flux linkage. Flux linkage is basically the total flux passing through the coil having N number of turns. So we can also see from the experiments, and practically we can see that N phi is directly proportional to the current I. The more current is flowing through the coil, so more flux linkage will be there across the coil. And converting this proportionality into an equation, we can introduce the constant N, which is a symbol for the self-inductance or self-induction. So we can simply write N phi is equal to Li. So we can put this value of Li instead of this N phi here in this equation, and we can change this equation here into this one, so that EMF is equal to delta over delta T into Li. We have put the value Li instead of N phi from this equation. Or we can take this L outside, which is a constant of proportionality, and it is a symbol used for self-induction. So we can take L outside and finally write Faraday's law for self-induction in this form: EMF is equal to L delta I divided by delta T. What is L? To explain L is basically the inductance of the self-inductance symbol for self-induction. The unit of self-induction is Henry, and it is symbolized as capital H. From this equation, we can write that N phi is equal to Li. We can find the value of L, which can be written like L is equal to N phi divided by I, the current I. So, that's all. Have a nice day. Thank you.